Hello students, welcome to class 11 physics class. Today we start a new chapter, that is nuclei. In live class we complete the chapter atom. Now today we start this chapter, that is nuclei. As we know that nuclei, each and every atom consists with the nucleus, and nucleus also always positive charge, positively charged. Inside the nucleus, proton and neutrons are there. Neutrons are neutral particle, no charge is there. Protons are positive charge particle, that's why nucleus is positively charged particle. The atomic radius is larger than the nucleus radius. The atom's radius is larger than the nucleus radius because nucleus is a part of an atom. So obviously the radius of the atom is always larger than the nucleus radius. The atom consists of neutrons which have the same mass as protons. The protons and neutrons are bound together by a nuclear force inside, and not the atom. This is called the nuclei consist of. Sorry, here you correct please. The nuclei consist of neutrons which have same mass as protons. The protons and neutrons are bound together with a nuclear force. So the entire positive charge and nearly the entire mass of atom is concentrated in a very small space, that is called nucleus of an atom. So nucleus is a part or the point where we consider the all mass of an atom is concentrated. The nucleus consists of protons and neutrons. These protons and neutrons together are called nucleons. Together are called nucleons. Okay. Now, before we discuss in details, first of all, we have to we an idea about the atomic number, mass number, and nuclear mass. Atomic number is the number of protons in the nucleus. The amount of protons present inside the nucleus, that is called atomic number, and this atomic number is denoted by Z, capital Z. Mass number is the total number of protons and neutrons present in a nucleus. Because nucleus is consists with protons and neutrons, so total amount of protons and neutrons, or you can say the total number of nucleons present in a nucleus, is called mass number. It is denoted by capital A. So from this two we can easily find out the number of neutrons present in an atom, that is A minus Z, because Z is the number of protons and A is the number of protons and nucleons together. So if we subtract from A and Z, from A and Z, A minus Z, that is gives us the number of neutrons in an atom. Clear? Okay. Now nuclear mass. Nuclear mass, the total mass of the protons and neutrons present in the nucleus, is called nuclear mass. Total mass of the nucleons present in a nucleus is called nuclear mass. Nuclear means mass of the nucleus. So nucleus consists with protons and neutrons. So the total mass of protons and neutrons or the nucleons is called nuclear mass. Now, as we discussed that the nuclear radius is smaller than the atomic radius. Nucleus size. Like an atom, the nucleus is not a solid object. Its surface is not a well-defined boundary. Still, we can assign the size of the nucleus. In the chapter of atom, we discussed the scattering experiment using high-energy probes such as fast-moving protons, neutrons, electrons. Nucleus size of different elements have been accurately measured. So experimentally, it is observed that the volume of nucleus is directly proportional to its mass number. During that experiment, it is observed that the volume of the nucleus is directly proportional to its mass number. So if we consider the radius of the nucleus is r having mass number a, so we can say that the volume is 4 by 3 pi r cube is proportional to a. So r proportional to, because 4 by 3 into pi, this is also be a constant. So we can write r proportional to a to the power 1 by 3. A to the power 1 by 3. Thus, the radius of the nucleus is proportional to the cube root of its mass number. So, we can write r equals to r0 into a to the power 1 by 3. In place of proportionality sign, we use the equal sign by multiplying a constant number, that is r0. R0 is the constant. It is known as nuclear unit radius, and its value depends on the nature of the particles. Which particle we use? The protons, neutrons, fast moving protons, neutrons, electrons. For electrons, its value is 1.2 Fermi, or 1.2 into 10 to the power minus 15 meter. Clear? Okay. Now discuss about the nuclear force. The average separation between the two nucleons, that means proton and neutrons, it is about 10 to the power minus 15 meter. At this separation, positively charged proton feels a strong Coulombic repulsion. Also, the gravitational force of attraction between two nucleons is smaller than the electrostatic repulsion. It cannot be hold the nucleons together. So there must be something strong attractive force acting between the nucleus that overcomes the electrostatic repulsion. This strong attractive interaction acting between the nucleons is called nuclear force. Is called nuclear force or strong interaction. So nuclear force is a strong attractive force that binds proton and neutrons together inside a tiny nucleus. Understand? Because neutron has no charge. So only the protons are there. Protons are positively charged, and positively charged particles repel each other. As well as there is a gravitational force of attraction also be present, and the electrostatic repulsion also be present. So to overcome this electrostatic uh, repulsion, there must be strong attractive forces acting between the nucleons. That's why they will not repel and they will not um, comes out from the nucleus. This strong attraction between the nucleons is called nuclear force. Okay, and in generally it is found that the one tiny particle is exchanged between a proton and a neutron. Okay, and when it will be exchanged, a proton will convert it to neutron and neutron will convert it to proton. So like this way, this strong attractive force will be generated, and that small particle is called meson particle. A meson particle will be exchanged in between proton and neutrons, and when it will be exchanged from proton to neutron, the neutron will be converted to proton and proton will convert it to neutron. Again the meson particle will be exchanged between them, then again proton uh, inverted to uh, uh, neutron, and neutron converted to electron, sorry, proton. So and due to this interchange of exchange of meson particle, a force, strong interacting force is act, that is called nuclear force or strong interaction. Now Einstein's mass energy equivalence. We know this very well famous equation, E equals to mc square. C is the speed of light in vacuum. Its value is 3 into 10 to the power 8 meter per second. This equation expresses equivalence between mass and energy. We know that it is a very important one equation. This equation suggests that even a particle is at rest, Rest means zero kinetic energy. Still possesses an enormous of energy because of its mass. A mass of particle measured in a frame of reference in which particle is at rest is called rest mass, and rest mass is denoted by m0. Rest mass is denoted by m0. This rest mass you study in highest classes if you study with relativity. Relativity is one uh, branch of a physics where we discuss this frame of reference rest mass. So you also studied these things in a relativity. Einstein relativity equation also be there. Einstein, all these things are discovered by Einstein. So one branch, separate branch also be there, one topic, that is relativity. So the total energy of the particle, we can say that it is a sum of rest mass energy and its kinetic energy. That means E equals to m0 c square plus t. So it is clear that most of the particle is greater when it is in a motion and then when it is at rest. Most of the particle is greater. Mass of a particle is greater when it is in motion, when it is at rest. Okay. The law of conservation of mass energy states that the sum of mass and energy of a system of particle is the same before and after their interaction. This is called mass energy conservation. We know that conservation of mass, conservation of energy. Separately we studied. Now this is the law of conservation of mass energy. Before and after the interaction, the total sum of mass energy of a system of particle is say, constant. Okay. Now we discuss another one term, that is mass defect. It is found that in the mass of stable nucleus is always less than the sum of the masses of its constituent protons and neutrons, because we know that the nucleus is consist with protons and neutrons. So the total mass of that nucleus, it is in generally it is equal to the sum of the mass of proton and sum of the mass of the neutrons, but it is not happening. Experimentally, it is shows that the total mass of a stable nucleus is always less if we separately weight the mass of the if we separately calculate the mass of the proton and mass of the neutron, and then if we added it, then the total mass of the nucleons it always less than the sum of the mass of its constituent particles in their free states. So this difference between the rest mass of the nucleus and the sum of the rest mass of its constituent nucleons is called is mass defect. That is called mass defect. As a total, suppose its mass is 10 kg, but if when you separately you measured it, the mass of protons suppose 8 kg and the mass of neutrons are 5 kg. So 8 plus 5, that total mass will be 13 kg, but in experiment it is shows that the total mass of that nucleus is 10 kg. So one defect is arise. Okay, that defect is called mass defect. So how can we find out the mass defect? Mass defect will be denoted by delta m. Delta m equals to ZMP. Z is it has Z protons. Suppose any nucleus here we consider X is the nucleus whose atomic number and the mass number are given A and Z. So Z protons and A minus Z neutrons. We know that how can we find out the neutrons? A minus Z. Therefore mass defect will be defined as delta M equals to ZMP plus A minus Z into Mn minus M. ZMP, that means the mass, atomic mass into the mass of the proton. A minus Z means the neutrons, number of neutrons. Z is the number of protons. Number of protons into protons mass plus number of neutrons into neutrons mass minus M. M is the mass of nucleus or mass of the nucleus X. That is a mass defect. Now the nuclear reaction. In this year, the radioactivity, this that portion is deleted. Okay, so this chapter is very small. In this one video, it will be completed. Nuclear reaction, the reaction that involves the change in the identity or the characteristics of an atomic nucleus induced by bombarding it with an energetic particle, is known as nuclear reaction. The bombarding particle may either be an alpha particle or the gamma ray proton or neutron or proton or heavy ion. Okay, this total procedure, because here we use the nucleus, that's why it is called nuclear reaction. Sorry. There are two types of nuclear reactions are present. One is a nuclear fission and nuclear fusion. Nuclear fission, when the nucleus of an atom splits into two light nuclei. One big nuclei splits into two light nuclei through a nuclear reaction. The process is termed as nuclear fusion. Fission. Okay, this is the experiment. Here, nuclear fission, we use the uranium 235 92, and it is bombarded with a fast moving neutron. So it is split into two light nuclei. One is a beryllium, another one is a krypton. 13956 and another one 9536, and another also two neutron also be generated. Then again these two neutron will be hitted the next at nucleus of the uranium 235 92. Then again it will break into light nuclei, beryllium and the krypton. Okay, Ba and krypton. This is the equation. An example of nuclear fission, splitting of uranium 235. The equation is given like this way: beryllium 144 or plus krypton plus 3 neutrons. Here one, actually in this procedure, whenever one first neutron is bombarded with a uranium 235, the 3 neutrons are generated. That's why here we write 3 neutrons plus heat will also be generated, that is 210 MeV. Another one example, if uranium 233, then we get this equation. Okay. Nuclear fusion. Nuclear fusion is opposite to the nuclear fission, where two light nuclei combine together and to form a single heavier nucleus is called nuclear fusion. Fuse together. Okay, and this is the very example is a deuteron, positron, and this is the examples of nuclear fission. 1H1 plus 1H1, it will form fuse together, it will form 2H1 plus 1 electron is there, one nu is there. Okay, and 0.42 MeV energy also be released. Similarly, if two deuterons combine each other, they will form a isotope of helium and a neutron, or a tritron and a proton, and a proton, and also be the some energy, some amount of energy. This will be the examples of nuclear fusion. Okay, so after this, these things are included in your syllabus in this year. Okay, so if you have any problem, any place, if you don't understand, please write in a comment box. Thank you very much. Have a nice day.